My name is Akriti, and I'm co-presenting here today with Avesh. And we'll talk about most common data challenges that you face in productionizing ML models and how you can solve it using Databricks Feature Store. I work at Databricks as an engineer on Databricks Feature Store. And before Databricks, I come here from Google, where I worked in Google Cloud and Google Research, building distributed systems and ML infrastructure. And to kick us off for this talk, I want to introduce Avesh.
Hey folks, my name is Avesh, and I'm also an engineer at Databricks. Prior to this, I was working on information retrieval at Google, and I was leading a small ML applications team at a startup. So Akriti and my backgrounds in distributed systems and machine learning motivate why we're interested in feature stores. When I started working in ML applications, feature stores didn't exist. So I've personally faced many of the challenges that we're going to talk about today. And in fact, in designing Databricks Feature Store, we specifically set out to solve these challenges. The thesis of this talk is that Databricks Feature Store enables your ML projects to reach production. We're going to start off by talking about what makes productionizing ML projects so hard. This is going to lead us into the 4 major data challenges that data scientists face when productionizing their ML projects. Then we'll introduce Databricks Feature Store, the first feature store built on top of the data lakehouse. And rather than talking about the feature store in slides, we're going to show you how it works in a demo. And finally, we'll conclude the talk, and we'll leave a couple of minutes for questions at the end. So let's get started. So what is it that makes production machine learning so hard? According to a VentureBeat article, 87% of machine learning projects never make it to production. But ML models are just code, and data pipelines are also just code. So doesn't this problem reduce to productionizing software? And we have a lot of experience in productionizing software over the last 40-some years in this industry. We code review prior to merging or releasing code. We write unit tests, integration tests, end-to-end tests to ensure that our code operates as expected. And then we run those tests automatically on merging code and on releasing code. Then when it's time to release, we're sure to release to staging first. We let projects bake in staging before releasing to production. And then when in production, we have monitoring and alerting to ensure that the code continues to run as expected. So why can't we do the same thing for machine learning? Well, we do. But there's a new dimension to this problem when it comes to productionizing machine learning, and that's data. Data is the lifeblood of machine learning, but data is also the most difficult problem that data scientists face in industry. Data scientists spend a majority of their time searching for data, getting access to data, and maintaining data quality. So now let's dive into a few of the biggest data challenges in production machine learning. To train a model, data scientists will start out with raw data sources. These are then joined, aggregated, or otherwise transformed into inputs suitable for machine learning, also known as features. However, after training, these data transformations and the raw data are often discarded. They're easy to forget about. But these assets are essential for reproducibility and for model retraining. Moreover, because features are not easily discoverable, the whole process is going to be repeated by other data scientists, even if the features they need are identical. This results in a lot of spaghetti code and technical debt. So this is the first major challenge of machine learning in production. It's difficult to find and reuse features because of data silos. Data science and data science teams store their features in different locations, in different file formats, and sometimes in places that are inaccessible to other teams. As a result, data scientists build redundant featureization pipelines. And this is just one part of a larger problem that's faced by enterprises today. Data is siloed between teams. Data used for business intelligence and analytics use cases is unavailable for data scientists, and vice versa. And this problem is generally solved by the data lakehouse. Because Feature Store is built on top of the lakehouse, it also solves this problem. But I'm getting ahead of myself. Let's move on to the next challenge. Once models are trained, they're ready to be deployed for real-time inference. Models require the same features to be used at inference time as were used at training time. However, oftentimes the services handling these requests need to have latencies in the tens of milliseconds, and the original featureization code just wasn't written to be so performant. So you'll often have production engineers rewrite the feature pipelines, sometimes in other languages like Java, in order to do real-time inference. Now the key here is that these transformations must be equivalent. Otherwise, the model is going to perform well in training and in evaluation, but it's going to perform poorly online in the real world because the feature values are different. This is a problem that's known as online-offline skew, and it's notoriously difficult to track down. So it's actually essential that you use the exact same features at training time as you do at inference time. And there's another problem that's similar to online-offline skew. When passing features, clients must read either the feature values or the raw data from some source. Now this is fairly straightforward for a single model, but in practice you'll often have multiple model versions in production. And these different versions are going to require different data. So it's essential that clients talking to a particular model version look up the exact data needed by that model version for inference. If they use the wrong data, the features are not going to be the same as used in training, and the models will perform poorly. We call this third challenge the client configuration challenge. Clients need to know which data to look up. And like issues with online-offline skew, the client configuration errors are very subtle and are very difficult to track down. And finally, the world is not static. Languages change, new products come to market, and customers change their location. Features must be kept up to date. Data freshness is the fourth major data challenge. For accurate predictions, models must be trained and evaluated on fresh data. And rather than computing your data just once, feature updates need to be streamed or need to be scheduled in batch. These challenges need to be addressed at a platform level, and we think that Databricks Feature Store is uniquely suited to solve them. It's the first feature store built on top of the data lakehouse. Data is stored in the open format Delta, and it's accessible by either Python or SQL. So what that means is that your features can be used not only by data scientists, but also for analytics and BI use cases. The data sources are also kept in the data lake. So your features, your data pipelines, your source data, and your models can all be co-governed in one platform. Feature Store is integrated with Spark, enabling automatic lineage tracking. And finally, it's integrated with MLflow, which means that the feature metadata is associated with models that were trained using those features, enabling not only a full lineage story between features and models, but also enabling models to look up feature values at inference time. And because Databricks Feature Store is built on top of the lakehouse, it fits into your existing data architecture and solves the previously discussed challenges. To show you this, let's now walk through an example of using the Feature Store in production. In this demo, Akriti is a production engineer, and I'm a data scientist at Bon Voyage, the world's premier travel booking website. As travel opens up around the world, Bon Voyage is excited to recommend new destinations to you, our user. We're building a sliding carousel of vacation destinations that are customized for each of our users. As a data scientist, I'm tasked with creating a model to recommend destination cities to existing users. So let's start off by finding some features for this model. Every day when I walk into Bon Voyage's office, I see this chart displayed on a giant projector. Actually, displayed on two giant projectors. And what this chart is displaying is popularity metrics. It's showing the hottest destinations according to TikTok and Instagram posts. So this seems like a pretty good source of features for my model. So I went ahead and talked to the business intelligence team that's responsible for creating this chart. And they told me they're using Delta Live tables to keep it up to date. So let's take a look at that Delta Live tables pipeline. So here we can see that the Delta Live tables pipeline is pulling in data from Instagram and TikTok logs, and is then computing virality metrics that indicate which destinations are super popular right now. This data is then streamed into the destination popularity table. So we could take a snapshot of this table and use that in model training, but if we did that, the features would no longer update, and moreover, other data scientists wouldn't be able to use these features in their machine learning models. So instead, let's update the Delta Live Tables pipeline to write to the feature store. So in this notebook, you're going to be able to see a definition of the Delta Live Tables pipeline. This includes our source data, like the travel destinations table, as well as the TikTok and the Instagram logs. And at the very bottom here, you can see that we're using Delta's continuous data capture to stream data into the destination popularity table. To transform this into a feature table, all that we have to do is modify the function call. We're going to instead call create feature table, and we're also going to provide a primary key, which is the destination ID, as well as a timestamp key, because these viral destinations change frequently, and so is the time series feature table. So after rerunning this pipeline, we'll see that a new feature table was generated. And here it is in the Feature Store UI. The destination popularity feature table includes features like the number of Instagram likes in the last hour or the number of TikTok posts. And we can see that it's being kept up to date by this Delta Live Tables pipeline, which is continuously streaming data into the feature store. So this looks like a nice set of features to start with, but we're going to need some more. So let's take a look in the Feature Store UI and see what else we can find. Great. It looks like this destinations features feature table may be useful for our problem of recommending destinations to our users. It looks like this feature table is created by a sister data science team of ours, the demand forecasting team at Bon Voyage. And we can see that it's actually kept very up to date. While it was initially created by this notebook, there's a recurring job running every night at 1 a.m. to update the feature values in batch, and it last succeeded last night. And looking at the features, it includes things like the average hotel price for this destination, or the COVID case counts for this city, average over the last day, or 30 days, or 7 days, as well as values pulled in from our website, like the average review, or the number of purchases over the last day. And these features seem like they're being used a lot. We can see all of the models, the model endpoints, and the notebooks that are currently using these features. And that indicates they probably have some salience for machine learning. So now that we've found some features, let's go ahead and train a model. In this notebook, we're going to train our model that recommends travel destinations to our users. We'll start off with the ground truth data, which is the vacation purchase log. So this includes for each user and each destination they were shown, the time when they were showing that destination, and whether they subsequently purchased a vacation to that destination. Let's now join in some features into this raw data so we can train a model. We're going to pull in all of our features from the destination popularity table, which is that table we just saw that was being kept up to date by Delta Live Tables. And we're also going to pull in the destination features. And finally, there's a number of user-specific features we would like to use. In particular, I think that the country will be useful, because that indicates how far someone has to travel to this destination. And I also think that COVID risk scores will be useful, assuming that COVID-conscious customers will not want to travel to COVID hotspots. In order to create a training data frame from this, we'll call the create training set method. And what this method does is it takes our feature tables and it performs an as-of join with our raw data. What that means is that for each row of the raw data, we pull in the latest feature values that were available prior to that timestamp. Feature Store generates this as-of join automatically, and so it ensures that you're never accidentally training on data from the future. We can take a look at the resulting data frame from this training set. And you can see here that it includes all the feature values, like the number of likes and posts on Instagram, or the COVID case counts, or the country of the user. And now that we have this data, we can train our model. We're going to use a very simple gradient boosted decision tree here and train the model. And then afterwards, we'll log the model to the MLflow model registry under the name destination recommendations. So let's take a look at this model in MLflow. So on this page, we're going to be able to see all of the metadata for this model. And we can see that Feature Store has added some specific metadata that lists out all of the features that were used in training this model, like the average price. And this metadata is going to be used not just for lineage from features to models, but it's also going to be used at inference time, which is what I'll show you next. So we're going to score this model on a test set, which is just 25% of our source data. And this test set, again, just has the user, the destination, the timestamp, and whether they were purchased, whether the destination vacation was purchased. We don't actually provide any feature values here. We're going to call the feature store score batch method and pass in that data frame, as well as the name of the model to score. And notice that, again, we don't list any of the features or provide any feature values here. What score batch is going to do is it's going to take a look at that model metadata and identify all the feature tables that are needed for this model. It'll then do a point-in-time join with those feature tables in order to generate a very wide data frame with all the features needed for model inference. Finally, the model will be scored on that data frame, and we can see the result, which has a prediction. And that's what's shown down here. This data frame includes our user, our destination, as well as all of our feature values, and finally, the model's prediction. So these feature values can be pretty useful in debugging the performance of our model. Now let's check the accuracy of our model. To do this, we're going to just choose a cutoff point and calculate the classification accuracy, and it looks like it's 87%. That's not bad, but I think we can do better. So I'm now going to invite Akriti, a production engineer at Bon Voyage, to try out some real-time features to improve the accuracy of this model.
Thanks, Avesh. You must all be thinking, what are real-time features? Real-time features or on-demand features are the ones that are only available at the time of the inference request. So let's take some example of real-time features. You can think of whether the user is on mobile device or a laptop. That would change the behavior of the user, and that would be a real-time feature for us. Some raw session data, like how the user, what pages has user visited in the past 5 seconds, that could be real-time feature. Sometimes at Bon Voyage, we do want our users and our models to behave according to the user. So as you can see in this diagram, like I was talking to one of the data scientists in the team, and she informed me that the longer the user looks at the destination, the more interested they are in purchasing that destination. We will call this feature destination view duration or impression duration. And impression view duration is the real-time feature that we would want to use in our pipeline. However, there are some challenges to this. So for example, as you could see here, if I use destination view duration, I might have to create 2 separate pipelines, one at model training time and one at model serving. The featureization code would have to be separate in the 2 parts. And this introduces a couple of problems for us. We have to re-implement the feature. This might cause online and offline skew that we were talking about earlier. And this also introduces tech debt to our code. So ideally, I would want to avoid duplicate code here. This is OK, because we could use MLflow PyFunc here in order to featureize our data together. So MLflow PyFunc is a way to featureize, to package your model such that you could include any custom computation to your code, to your model. So you could see on the left here, we have on-demand feature computation. And that you could use that on-demand feature computation both at the training time or at the serving time. And this would take your raw session data, like impression duration, and it would featureize that and pass that into the model on the right, which is the box that you see on the right-hand side. So let's see how this will work in our code. I have defined an on-demand computation model wrapper over here. This model wrapper is an MLflow PyFunc. And you could see that I have defined a pre-processing or a custom featureization code in the bottom over here. At the training time, I'm calling the pre-processing on every data frame and then calling train. And at the predict time, I'm calling pre-processing. So this is the same featureization code and calling model predict. Being able to utilize the same code to perform featureization at the training time or at the inference time helps me to reduce the online-offline skew as well as the tech debt. And this way, we are able to remove some of the issues that we talked about earlier. Great. So now our model can learn from the real-time user behavior or on-demand user behavior. I was thinking how to improve the model even further, how to make vacation purchases like even more. And I was talking to the growth team at Bon Voyage. And one of the data scientists informed me that sometimes users are more inclined to purchase a vacation if there's some sort of urgency. For example, if the hotel availability is running low. However, there is a problem if I only get the features at low duration. So if we can see here that we can think of a batch pipeline here. But what the batch pipeline would do is it would be too slow, and it would stream in features, and our features would be, super old and cause the predictions to be out of date. So I want to continuously stream this data. So it would be great to continuously stream in the data here. Because of seamless integration of Databricks Feature Store with Spark structured streaming, I could define any data source that Spark structured streaming supports, like Kafka or Amazon Kinesis, to stream in data to my offline feature data and also publish that to the online store. We'll talk about that in a little while. Before that, let me show you the code over here. So we are using the Kafka streaming data source, and we are creating a streaming data frame. The feature store write table call can take in any streaming data frame and create a job that would continuously stream your features to the offline data store. This way, I'm able to keep all of my features fresh in the feature store and train based on the fresh features. Thanks to Databricks Feature Store, I do not have to create a separate infrastructure in order to keep my features fresh. Let's retrain our model with the new features, like the on-demand features that we just created now, and the streaming features. We added impression duration as an on-demand feature. So let's see if that is already there in our ground truth. So we can see that impression duration is here in our ground truth. Also, we can see that we added the destination availability over here. And destination availability was our streaming feature. This was the hotel availability that we were streaming from Kafka. Let's create a training set with the new features. And here we can see that our training set is created with all the new features. Now let's train our model so that our model can use the on-demand computation model wrapper. As we saw earlier, the on-demand computation model wrapper would featureize the real-time feature or on-demand feature into the feature data. And we will log the model using feature store log model. Using feature store log model helps us because, as we talked about earlier, it makes the model aware of features in training time. But not only that, it also makes the model aware of online store and all the required features over there. We'll talk about that in a minute. Great. So now we have our model with fresh feature data and real-time feature data logged. Now let's evaluate this model and see how it performs. For this, I'll use the score batch API. And we could see that the model accuracy had increased from 87% to 93%. So what's next? For Bon Voyage, we need the model to do low latency predictions, since we need to show fresh recommendations to the user each time they visit our website. Real-time applications, for this, they need very low latency lookup. And they want a fast key value store for feature table lookup like DynamoDB. However, the storage schema for my offline table would be different from the storage schema for my online table. So I would have to write a pipeline to do the conversion. Thanks to Databricks Feature Store, I do not have to write this conversion code anymore. Databricks Feature Store provides a simple API to push features from the offline store to the online store with a simple one-line API call. It pushes the feature because it pushes the features that were used at the training time from the offline store to the online store, which is used at the inference time. We also reduce any offline-online data skew that we talked about earlier. Let's do a code walkthrough here. So here I'm creating an online spec using the Amazon DynamoDB. And I'm calling the publish table API with the offline table that I want to push to the online store. As you can see here, since we are publishing to DynamoDB, there are many other online stores that are also supported. So we also support other connectors to sync the data. And because we are using, we are running, Databricks Feature Store runs over on the top of Spark. It leverages Spark's parallelization for parallel updates and fast updates. So now, let's look at what happens to the table here. So destination availability was one of the table that we published. And destination availability, if you remember, it was one of the streaming table. We can see that the online store for that is in DynamoDB, since we use the DynamoDB spec. And when we click through it, we could see that there is some metadata associated with it. And one of them is region, which is US West 2. This is great because our web application is also deployed in US West 2. So we will have low latency lookups. And you could also see that there are a bunch of published features over here, which is hotel availability and attractions availability. In order to enable streaming updates, all we have to do with the publish table API is set the parameter streaming as true. And this will kick off a job that would continuously update the features in DynamoDB, which is our online store. Great. So now we have our all the offline features pushed to online features, so we can do low latency lookups. What's remaining? In order to create the web application, I also need to do low latency predictions. For that, I would have to host my models somewhere. Thanks to Databricks model serving, that makes it super easy for us. But what else do we need? We also need to update our application code in order to talk to the updated version of the model from before. And for that, I would have to see what is the delta in the features that the new model uses over the old model. And all of this complexity would lie in the web application. As we talked about earlier, this also causes a lot of client configuration issues that ideally we do not want to deal with. Because Databricks model serving is co-designed with MLflow and Feature Store, we already track all the lineage information of the features and the online store within the model. So when you do a model when you call the model scoring API, it simply calls all the lookup by itself because it has the lineage information, and then it calls the store. So let's see how we can do this through Postman. Here, I'm calling my model endpoint, and I've specified all the primary keys over here. So I have user ID, destination ID, and impression duration. And let's send the request. All right, so we see that the score returned from the model is 25%, which means for this user, for this destination, there's only 25% likelihood that the user will buy this destination vacation package. So we are not going to recommend this to our user. Thanks to Databricks model packaging format, this significantly simplifies the client logic for me when upgrading the application code. The user code no longer needs to maintain any lookup or computation logic or handle any configuration management. Our user has to only deploy the model and call the scoring API. That's it for our demo. In summary, we saw how Databricks Feature Store solves many of the data challenges that you face in productionizing your ML model. First, we saw how we broke down data silos using the lakehouse through a central feature store repository. Then we used Delta Live tables to enable production-grade data pipelines. We also eliminated offline and online skew by pushing features from the offline store to the online store. Next, we solved the challenge of data freshness using Spark structured streaming with Feature Store. We also enabled on-demand computation of features with MLflow PyFunc. Lastly, in order to do model serving, we solved the challenge of client code configuration through using model serving that was co-designed with MLflow and Feature Store. Thank you so much for being here today, and we will now take any questions that you might have. Also, we'll be standing outside of this room after the talk in order to discuss your ML use cases more.
I think we're out of time, so we can take the rest of the questions outside. One important plug, there's a really great talk after this by Casey and by Prem on ML in the Lakehouse. So everyone in this room, I would recommend coming back to watch it. Folks online, please tune in or watch the recording. But yeah, thank you so much.